You're crossing a massive bridge suspended high above a vast expanse of water. Below you, hundreds of meters down, the seafloor is hidden from view. The water churns and shifts. Yet somehow, this enormous structure remains solid and stable beneath the weight of countless vehicles. It seems impossible. How did anyone engineer something so monumental? How do you build a foundation in the middle of a moving river? How do you construct towers in water deeper than tall buildings are high? The answers reveal some of humanity's most impressive engineering accomplishments. Bridge building is ancient. For thousands of years, humans have spanned rivers and valleys with wooden beams and stone arches. But crossing deep water presented fundamentally different challenges. The breakthrough came during the Industrial Revolution. Steel offered greater strength than previous materials. New technologies allowed workers to operate underwater. The Brooklyn Bridge, completed in 1883, demonstrated that even dramatic water crossings were possible. Modern engineering has pushed this further. Today's bridges span impossibly wide channels and cross depths that would have seemed unimaginable to earlier engineers. The choice of bridge design depends on multiple factors: how far it needs to span, how deep the water is, what environmental forces it must withstand, and budget constraints. Different designs excel in different situations. Beam bridges are simple and effective for shorter distances, but they require support columns, which become impractical in deep water. Arch bridges distribute weight through curved structures, making them efficient but requiring specific conditions. Suspension bridges work best for very long spans. They use massive cables hung from tall towers to support the roadway. Cable-stayed bridges are often more economical than suspension bridges for medium to long distances. The cables connect directly from towers to the deck, reducing the number of towers needed in the water. The real engineering challenge begins with foundations. Every bridge requires stable support, but achieving this underwater involves remarkable ingenuity. Engineers employ several proven methods. Cofferdams are temporary enclosures, giant watertight boxes made from steel walls. Workers drive these walls deep into the seafloor, pump out all the water, and create a dry workspace. Inside this artificial dry area, crews construct foundations exactly as they would on land. It's like creating a temporary island. Caissons work differently. These are massive hollow structures. Imagine enormous concrete boxes that are carefully lowered into the water. Workers inside excavate material from the bottom, allowing the caisson to sink deeper. Once it reaches stable ground, the caisson is filled with concrete, becoming a permanent foundation. Pile driving is another method. Long steel or concrete columns are driven deep into the seabed using powerful hammers. These piles transfer the bridge's enormous weight to stronger geological layers far below. The deeper the water and softer the bottom, the longer the piles must be. Once foundations are secure, workers begin building the bridge's towers or support piers. These structures must withstand tremendous forces simultaneously. The bridge's massive weight, traffic loads, powerful wind pressure, water currents, and temperature changes. Building these towers requires precision and care. Most towers are constructed section by section, built upward gradually. Modern construction techniques use climbing systems that allow workers to progressively build higher. Prefabricated components are assembled on site, speeding the process. For extremely tall towers, engineers use advanced monitoring systems to ensure perfect alignment. Even small positioning errors can compound and create major structural problems later. The bridge deck, the actual surface where vehicles travel, must be constructed with remarkable precision. Methods vary depending on the bridge type. Segmental construction involves fabricating deck sections on site or in factories, then lifting them into precise positions. These sections must fit together nearly flawlessly. Balanced cantilever construction is used for some bridges. Sections are added to towers equally on both sides, like balancing arms on a scale. This approach keeps weight distributed evenly as construction progresses. For suspension bridges, cables are installed first, then the deck is hung from them, section by section. Tolerances are often measured in millimeters. The amount of error allowed is incredibly small. A misalignment of a few centimeters across hundreds of meters can cause serious problems. For long-span bridges, cables are the structural heroes. These aren't simple ropes. Each cable consists of thousands of individual steel wires twisted together, creating extraordinary strength. A single cable from a major suspension bridge can support tens of thousands of tons. The cables distribute weight efficiently across the entire structure, making long spans possible. Without this cable support, bridges stretching across miles of water would be impossible. Bridges in aquatic environments face relentless stressors. Wind is one of the most serious threats. The famous Tacoma Narrows bridge collapse of 1940 occurred partly because engineers underestimated wind effects. Modern designs carefully consider aerodynamics. Engineers shape bridge components to minimize wind-induced vibration. Water presents its own challenges. Salt water causes corrosion, slowly damaging steel and concrete. Engineers combat this with protective coatings, specially formulated concrete mixes that resist salt damage, and drainage systems that minimize water penetration. Regular inspection and maintenance programs catch deterioration early. In some regions, earthquakes pose significant dangers. Modern bridges in seismic zones include flexible design features that allow some movement. These systems absorb and dissipate the energy from earthquakes rather than fighting it rigidly. The structure sways slightly but doesn't break. Before a bridge opens to the public, it undergoes comprehensive testing. Sensors are installed throughout to monitor structural behavior. Engineers load the bridge with weights equivalent to expected traffic. Sometimes fleets of heavy trucks are positioned across the entire span to test how the structure responds. Engineers measure deflection, vibration, and stress. They verify that every component behaves exactly as predicted. Only after successfully passing these rigorous tests does a bridge open to traffic. Modern bridges represent the culmination of centuries of engineering knowledge. They're built using materials that didn't exist 100 years ago. Construction techniques would seem miraculous to earlier engineers. Yet the fundamental challenge remains unchanged, creating stable structures across unstable water in difficult conditions. The next time you cross a bridge over deep water, take a moment to appreciate the engineering beneath your feet. That seamless roadway represents years of planning, thousands of workers, advanced technology, and extraordinary human ingenuity. Underneath that smooth surface lies an invisible network of foundations, cables, towers, and systems, all working together to keep you safe. It's a reminder of what humans can accomplish when we combine knowledge, creativity, and determination. Thank you for exploring bridge engineering with us. Subscribe to discover more hidden engineering marvels, and tell us what topics you'd like us to investigate next. Stay tuned for more stories woven through the smallest details.